Go to SARC Study Union, sarcstudyunion.wordpress.com. It should be there in like the next couple minutes. But for now, I'm just going to be going over the problems that are in that review. Like chapters 1 and 2 are pretty easy, so I think you all should be able to follow along pretty easily. If you've been to my other sessions, I've already told you all, but this is not going to be like a regular SARC session, so you're not going to be able to ask as many questions just because there's a lot in this review and I want to make sure I can get through as much as possible. But if you do have questions, just write it down or star, and then we can talk about it once we get to the end if we have more time. But if you guys can't see or something, just let me know because, you know, this is behind me. Oh, why is it upside down? Assad, it's upside down. Oh, might be, guys. Okay, so the way I structured this review, I have like notes for each chapter and then some practice questions. We're not going to go through the notes, but we'll just start with the practice questions. So from chapter 1, you do have to do a lot of conversions, and that's actually a very important concept because you use it for a lot of your other math problems. So it's asking for us to convert 4 times 10 to the 6 nanometers to millimeters. And like I said, just let me know if you guys can't see it. So you do have to remember what your conversion factors are. 1 nanometer equals 10 to the negative 9 meters. But then you still need to convert that back to millimeters. And if you calculate, can you all see that? Not really? Assad, it's too bright. They can't see it. But if you do that, you should get 4 millimeters. I'll try writing in pen.
Alright, so like these 2 buttons on the side, this will make it darker and that'll make it brighter.
Okay. Is that better? Yeah. Okay.
Alright, so you can just adjust it based on.
All right, thank you. All right, so the second question asks for you to convert 1.8 quarts to cubic centimeters. And for this one, you have to remember that a cubic centimeter is the same thing as 1 millimeter. So if you do that, you should get 1.7 times 10 to the 3 centimeters cubed, which would be the same thing, as I said, as a millimeter. So that's mostly what you need to know from chapter 1, just how to convert from one unit to the next. Okay. All right, so from chapter 2, we're going to talk about atomic mass. So it asks, what is the atomic number, which is Z, mass number A, and the symbol of the chlorine isotope with 18 neutrons? So if you look at your periodic table, Chlorine is right here, and you'll see that it has an atomic number of 17. So you have 17 protons, but they already told you that you have 18 neutrons. So 17 plus 18 neutrons is going to give you the actual mass of 35. So then when you write it out, you get 35, 17 chlorine. And that's what it should look like. Okay, so for the second question, it says, copper has two naturally occurring isotopes, copper 63 with a mass of 62 and a natural abundance of 69%. Copper 65 has a mass of 64.9 and a natural abundance of 30%. Calculate the atomic mass. So basically for these types of questions, you want to change the number that they gave you, the percentage, first to a decimal. Then you want to take the decimal that they gave you and multiply it by the mass that you were given. And once you do the math for those, you should get 63.55 AMU. So basically that's just saying that's the mass that you get when you average those two values. Okay. Can you all see okay? No? Do I need to zoom in? Hold on. They still can't see.
I don't know what to tell you, to be honest.
They said if we can turn off the lights, maybe that would help.
Turn off these lights?
Yeah.
I don't even know how those work. I just get paid to point the camera. They want you to make it darker or brighter. Because if you turn off the lights, then
Is that better? Yeah? Is it better?
When I was a little bit,
Okay.
sit on the floor till I saw the sea.
Yeah. Okay. I think that's the best we can do, guys. Is the review up? Okay, if you go to sarkstudyunion.wordpress.com, it should be under my name now, under chemistry. sarkstudyunion.wordpress.com.
It says it doesn't exist.
They said it's still.
just refresh it. I just updated it. It's right there. So here,
Okay.
here's your laptop.
Thank you.
Let me see.
Is it UCF study?
Oh, it's UCF study. It's UCF study.wordpress.com.
Yes. It's under Luderve. Is it there? Yep. Okay. Okay, so if it's there now, you all should be able to follow along. I'm under chapter 2 on question 3. Okay, if you need help, Assad will help you, but I'm going to keep going. So question 3, it's asking how many copper atoms are in a copper penny with a mass of 3.10 grams? So you start, this is your stoichiometry. You start with 3.10 grams of copper. Compare that to the molar mass, to 1 mole of copper. And then use Avogadro's number to figure out how many atoms you have. And you should get 2.94 times 10 to the 22 copper atoms. He's trying to get them on the website. They should be up there.
Like you could do them like side by side or like on the same paper.
I don't think it's big enough for that. It's not going to be big enough for that.
Just try to do it like underneath the words, but
Okay. All right, so chapter 3. Most of chapter 3 is just naming. And that's actually a very important concept because sometimes your professor may ask a problem and not give you what the actual molecule is, and you're just going to have to go based off of the name and be able to figure it out. Okay, so for the first one, you have sulfur dioxide. And that's just how you name your nonmetals. The next one is an acid. So you have perchloric acid. And make sure for those that you study your polyatomic ions so that you would know that this part right here is your chlorate. And the next one is a transition metal. So you have to have the charge cobalt to fluoride. And if you don't remember these, I put the page number to where it goes over all of the naming rules. For the next one, you have iron. You have iron sulfate, FeSO4. Again, you need to know what your polyatomic ion is. The next one is hypochlorite. Hydroiodic acid. And the last one is nitrous acid or nitrous acid. And again, for that, you would need to know your OUS ending to figure out that that would be the nitrite form and not nitrate. Can you all see better? Yes, no? Yes. Okay. So if you have nitrous acid, that goes with nitrite. And if you have nitric acid, that's going to go with your nitrate. Okay? All right, so number 3 asks, calculate the number of grams of chlorine and 38.5 moles of CCl2F2. So they already gave us 38.5 moles of CCl2F2. Then you're going to do some stoichiometry and find for every 1 mole of that molecule, you have 2 moles of Cl in it. But we're still at moles of Cl, and it asks us for grams of Cl. So we need to compare it to the molar mass, which you can find in your periodic table, to figure out the grams of Cl. So you should get 14.7 grams of Cl. Okay. All right. So a compound has nitrogen and oxygen. It's decomposed and it produces 24.5 grams of nitrogen and 70 grams of oxygen. And it wants you to figure out the empirical formula. So this problem is a little long, but we're gonna get through it. So you want to start out first by taking the amount of each element that they gave you in grams and converting that to moles. And again, this is just stoichiometry, guys. And we had 70 grams of oxygen, and again, convert that to moles. So now you have your numbers in moles. So you write out the formula with the moles that it gave you. But as you can see, you normally never see a molecular formula like this. So what you need to do is divide it by the smallest number of moles, which would in this case be 1.75. And you will get but then again, you don't want a number like 2.5. You want a whole number. So what you're going to do is multiply by 2 to get that whole number. So you should get N2O5 for your empirical formula. Okay. Now, chapter 4. And if you all need more time to write it down, just let me know. All right, so chapter 4, we're going to get into our reactions. So here they give you the reaction. It gives you the amount that you're starting with, and it wants you to find limiting reactant, excess reactant, and your theoretical yield. Can y'all see that? I'm sorry, I'm just going to have to cover it up. Okay. So you started with 86.3 grams of NO. But if you're wanting to find theoretical yield, you need to find out how much product you could theoretically make. So to do that, you first need to convert to moles. So you use molar mass. And you do your mole to mole ratio. And as you can see, for every mole of NO, 2 moles of NO, you're going to have 2 moles of NH3. And if you do the math, you should get 2.8757 moles of NH3. It also told you that you have 25.6 grams of H2. You're going to do the same thing again and compare that to the molar mass, 2 grams of H2 per 1 mole of H2. And then in your equation here, 5 moles of H2 is going to be creating 2 moles of NH3. And you should get 5.0693 moles of NH3. So looking at these numbers, we can already figure out some of our answers. So if you're looking for the limiting reactant, that's going to be the one that creates the least amount of product. So in this case, this is the least amount of product. So NO is going to be your limiting reactant. .06 is the most amount of product, so H2 is going to be your excess reactant. And then it asks us for theoretical yield. Well, for theoretical yield, you have to figure out the answer based off of the least amount of moles that you can produce. So 2.8757 moles of NH3, since that's our limiting amount. And then we want to convert that to grams, just using molar mass. And that should be your theoretical yield. Okay, so for the second question, it asks, what volume of 0.15 molars of KCl solution will completely react with 0.15 liters of 0.175 molars of lead nitrate solution according to the following equation. So in this equation, we're going to start with the amount of lead nitrate that they gave us. I always suggest, if you have no idea like what to do on a problem, just write down what they give you and see if there's like maybe an equation that relates all of those variables. So always start with what you're given, and that should help you get where you need to be. All right, so we start with that much lead nitrate. And remember that molarity is basically your moles over liters. So we have 1 mole, for every 1 liter of lead nitrate, you have 0.175 moles of lead nitrate. And you just figure that out based off of the molarity that they gave you. Then you want to compare that using stoichiometry to the amount of KCl that you have. And then you do another multiplication because they wanted it in, not in moles of KCl, but the volume of KCl. So you need to get that using molarity again, 2 liters. And you should get 0.35 liters of KCl. Everybody found the review online? Yeah? And everyone can see, right? Okay. All right, so for question 3, it's asking for the complete ionic and the net ionic equations for each reaction. So for these questions, it's really important for you to know your solubility rules. And I believe I put in table 4.1 is where you're going to find your solubility rules. So make sure that you know that table, or it's going to be really hard to figure out problems like this. Bless you. 0.35 liters of KCl.
Where did you get the 0.15 from?
That should be your molarity of KCl.
Oh, it said that in the problem? Oh, I see.
Yeah, you see it? Okay.
Thank you.
All right, so this is the equation that we're working with, and it wants us to find the complete net ionic equations. So for your complete ionic, it's exactly what it sounds like. You want to write out everything as its ion, right? So this, what I'm writing on the second line is your product side. So this is everything written out as its ions. And then for your net ionic equation, you're going to cancel out your spectator ions, which is everything that you see on both sides of the equation. And once you do that, you should be left with this. So your CL's canceled because they were on both sides, and your lithium's canceled. So if it asks for spectator ions, it would be chloride, chlorine, and lithium. Okay, anyone still writing? Okay, so for chapter 5, I believe this is one of the chapters that you haven't had a test on yet, so I put a few more questions just to make sure that you all get this for the test. So the first question is really just asking about your gas laws. So it asks, as the temperature as the temperature of the gas increases, what happens to the volume? So as temperature increases, you know that it's going to expand, right? So your volume is also going to increase. And that's based on Charles' law. For the next one, as the volume of the gas increases, what happens to the pressure? So as you increase the volume, pressure is going to decrease. And that's going to be based on Boyle's law. As the amount of gas decreases, what happens to the volume? So the less gas that there is, the volume is also going to decrease. And that's Avogadro's law. So make sure you know your gas laws and like the concepts behind all of them. Okay, for number 2, okay. So it's telling you that there's a reaction occurring in this cylinder that has a movable piston. It tells you it produces this amount of product. It had 0.12 moles before the reaction and an initial volume of 2.18 liters. And then it's asking for the volume, the volume after the reaction. So to figure that out, again, I think it's best when you try to pick out what variables that they gave you and then figure out which gas law is going to use those variables. So for number 2, the initial amount of moles was 0.12 moles. The initial volume was 2.18 liters, and the final volume is what we're trying to find. So if they give you N and V, you should know that that's Avogadro's law. And the formula for that is V1 over N1 equals V2 over N2. So 2.18 over, and then from here, if you know the equation, from there it's just plug and chug really. And your final volume, you should get about 11.3 liters. Okay. All right, so for number 3, it asks for the volume, and it gives you the amount of moles, and it also gives you the pressure and the temperature. So right there, that should alert you that you need to use the ideal gas law, because it basically gives you all of the variables for that. So they gave you the number of moles. They gave you the pressure in millimeters of mercury. But you actually don't want it in millimeters of mercury. You're going to want to convert that to ATM. So you're going to have 760 millimeters of mercury to 1 ATM. You also have your temperature, which is 58 degrees Celsius. but you don't want it in Celsius. You want your temperature to be in Kelvin. So 58 degrees Celsius plus 273, and that's just always the number that you're going to use to convert to Kelvin. And you should get 331 Kelvin. And the thing that we're looking for is volume. So we have moles, pressure, temperature. R is a constant, and now we're just looking for volume. So you want to use your ideal gas law for that. Okay. So that's PV equals nRT, and we're solving for volume. And then once you have that equation, you're just going to plug and chug from there. So 0.556 moles times your constant, and if you all can't remember what units that your answer needs to be in, if you remember your constant, it has all the units there for you. So volume needs to be in liters, pressure in ATM, moles in Kelvin. I don't know why this is. Is that better? Okay, I'm missing a 0, but it shouldn't make that much of a difference in your answer. And then your final answer is going to be 16.2 liters. Okay, so number 4. All right, so this is also going to be one of our longer problems. So it gives you 1 liter of a mixture that has helium, neon, and argon. It has a total pressure of 602 millimeters of mercury, and the temperature is 298 Kelvin. The partial pressure of helium is 341, and the partial pressure of neon is 112. And it wants to know what mass of argon is present in the mixture. So first, we can write out our total volume equals to 1 liter. And in our solution, we have helium, neon, and argon. That's just a note so that we can remember that. I don't know why it's so blurry. Okay. They told us what our total pressure was. They told us our temperature was 298 Kelvin. Partial pressure of helium is 341. And of neon, it's 112. And then it wants the mass of argon. So first, we're going to start with our P total. That's going to be equal to our P total is going to be equal to the partial pressures of helium, partial pressures of neon, and partial pressures of argon all together. And luckily, they gave us all of those values. So P total minus partial pressure of helium and neon, and you should get 209 millimeters of mercury. So you just plug in the numbers for that. Then we're going to convert this number to ATM because we want to use it in our ideal gas law, and pressure has to be an ATM for that. So you should get 0.275 ATM. Then from there, if we use the ideal gas law and solve for moles, just plug in our numbers again. You should get 1.125 times 10 to negative 2 moles of argon. But again, we're not fully there yet because it didn't ask for moles of argon, it asked for the mass of argon. And this is just the same as what we've been doing this whole time. So if it gives you moles, you're just going to use molar mass to convert back to grams. So we'll use the moles that we just had. And compare it to molar mass of argon, 39.95 grams of argon. And we should end up with the mass of argon, 0.449 grams of argon. All right, so number 5, it gives you the reaction and it wants to know the volume of H2 in liters. It gives you a pressure of 748 millimeters of mercury, temperature is 86 degrees Celsius, and it wants to know, and it gives you grams of C3OH. And then the next part is just a separate question. So first I would start out again, writing out what they gave us. Pressure equals 748 millimeters of mercury. Temperature equals 86 degrees Celsius. Mass equals 25.8 grams of CH3OH. And it wants to know the volume of H2 in liters. So again, your ideal gas law, PV equals nRT, and we're going to solve for volume. Before we do that, sorry guys. Before we do that, we're going to have to change some of our units. So take your 748 millimeters of mercury times 760 to convert that. They also gave us grams of CH3OH, but we don't want that. We want it to be in moles of H2 in order to solve for volume of H2. So we're going to use stoichiometry. Compare that to the molar mass of CH3OH. But we can't stop there because then we're in moles of CH3OH, but we want it to be in moles of H2. And if you do that, you should get 1.61 moles of H2. So now we have our pressure, we have our moles. Now we can solve, oh well, temperature. Let's change that. 86 degrees Celsius plus 273, and you should get 359 Kelvin. Now we can use ideal gas law. PV equals nRT. We're solving for volume. And again, from here, we're just going to plug and chug. And once you plug those in, you should get 48.4 liters of H2. And then there's a follow-up question for number 5. And it asks, how many liters of CO gas? So if you could figure out the first part of this question, the second part of this question is pretty much the same thing. So we'll just do it really quickly. So if you want volume of CO in liters, you're going to do, again, you started with the same amount of CH3OH, but instead of going to moles of H2, you're going to go to moles of CO. And they're in a 1-to-1 ratio based on the equation. So this next step is not really necessary if you know what you're doing. And you should get 0.805 moles of CO. Then from there, you're going to do the same thing again. PV equals nRT, or V equals nRT over P. Plug in all your numbers, and you should get 24.2 liters of CO. All right, so number 6. All right, so the gas mixture contains 1.25 grams of N2, 0.85 grams of oxygen. It gives you the volume of 1.55 liters and the temperature. And it wants you to calculate mole fraction and partial pressure of each component. So I don't think your professor would ask you for all of this in one question. It'll probably just ask you for one of these because it is going to be a long problem, but you'll at least know how to do every part of this question. Okay. All right, so if we start with the mass of N2 they gave us was 1.25 grams. Mass of O2 is 0.85 grams. And volume is 1.55 liters. Temperature equals 18 degrees Celsius, but we can just change that to Kelvin right away. We get 291 Kelvin. So our mole fraction is what we're looking for, and our partial pressure is also what we're looking for. Okay, so the clue here is it says mole fraction. So even if you had no idea what to do, they gave you your values in grams. So you should know from there that you need to change to moles if you're looking for mole fraction. So that's what we're going to do. And then the same thing with oxygen, just compare it to the molar mass. And don't worry if you're off by like a couple decimals when you put these in yourself. I don't think that the answer is going to be that close to one another. Okay? But then for mole fraction, you want the number of moles of that element over the total number of moles. So then you just simply want to add those together. So moles of N2 plus moles of O2, and you should get about 0.072 moles total. And mole fraction is exactly what it sounds like. So if you want to know the fraction of moles of N2, you do moles of N2 moles of N2 over total moles. And you should get about 0.627. So that's already one of your answers right there. Now, for the mole fraction of the other one, there's two ways that you can do it. If you know that there's only two elements within the mixture, you know that both of them have to equal 100%. So you could just do 100% minus the mole fraction of the other one, and that'll give you the mole fraction of the one you're looking for. Or you can just do the same thing that you did again, and just do it again for O2. You get 0.373. These two answers, since there's only two elements in the mixture, should equal up to 1, right? So that's a good way to check your answer if there's only two elements in the mixture. But like I said, you could have just did 1 minus this, and that would have given you the answer. All right, so that's part of it. We got the mole fractions. Once you get the mole fractions, it should be easy to figure out what the partial pressures are. So you want to find first your total pressure because that wasn't given. And to do that, you need to find the total number of moles, which we already did. So P total equals N total RT over V. And you're just going to plug in the numbers that they gave you at the beginning. Do you have a question? Or are you stretching? Okay. That's okay. And that's going to give you 1.8 ATM. Once we find total pressure, you're going to use your mole fraction and multiply that by the total pressure to find the partial pressure. The mole fraction of N2 times the total pressure should give you the partial pressure of N2, which is going to be 0.687 ATM. Partial pressure of oxygen should be the mole fraction of oxygen times the total pressure again times 0.409 ATM. And these are your partial pressures. So that was a lot using the equations from chapter 5. So if you get that, that's probably a good review for that chapter, making sure you understand the concepts and how to use the equations. Mm-hmm.
Okay, is that the 1.8 is the total pressure?
Yes.
And then are the partial pressures supposed to add up to the total?
They should. Do they not?
No.
What'd you get?
1.096 when I added them together.
That's weird. When you add the partial pressures together, they should equal the total pressure. There may have been like an issue here with the calculations, but just try it again. But the method is correct, is what I'm saying.
Okay, so you just found the total pressure and then multiply that by the...
Mole fraction. Yeah. So if you do that, try it again at home. You should be able to get they should add up to equal the total pressure. Okay. So that was chapter 5. Chapter 6. Oops. So the first question gives you the equation, and it's asking you basically for the delta H. So it gives you a certain mass and then asks you for the delta H associated with that mass. Okay. So you start with 13.2 kilograms of C3H8, which is what they gave you. But we're simply going to change that to grams. 1 kilogram is 10 to the 3 grams. Now you have moles of C3H8. And we're going to do stoichiometry. I'm sorry, we have mass of C3H8. Now we're going to go to moles. And we're just going to use the stoichiometry for that. So molar mass to 1 mole. And that's going to give us how many moles of C3H8 we have. Then we need to compare that to the moles we have in the equation and the delta H that they gave us per mole. So for 1 mole of C3H8, it told us that the delta H was negative 2044. So that's how much, this is how much energy for 1 mole. Now we're finding how much energy for this amount of C3H8. And that should give you negative 6.12 times 10 to the 5. Okay, for the next problem, this is pretty much you doing Hess's law. So I'm not going to rewrite the equations. I'm just going to show you on here what you would do. So actually, I will write them. What I like to do is I take the equation, this equation that they gave you, and I know from there that that's what I want all of these other equations to equal to. So I'm just rewriting the equations. So the first equation has a delta H of negative 2043. And like I said, all of these equations need to add up to equal the original equation that they gave you. And this H right here is supposed to be an arrow, not an H. Okay, let's move this up. Okay. And that's going to equal the equation that we're looking for. And it wants to know what delta H of this equation is. So what we want is C3H8 on the product side, but in this first problem, C3H8 is on the reactant side. So we're going to flip this equation. So in order to get CH3H8 on the product side, we're going to flip the equation. Oh, this pen isn't. And if you flip the equation, you also need to flip the sign of your delta H. So this becomes positive. We also want 3 C's, but in our second equation, we only have 1. So in order to get 3 C's, we're going to multiply by 3. If we multiply the equation by 3, we do the same thing to delta H. We're going to multiply that delta H times 3. For the last one, oh, this should be 2H2. For the last one, we want 4H2, but we only have 2H2. So we're going to multiply that last equation times 2, multiply the last delta H by 2. And then when we add up all these delta H's, it will give us the delta H of the equation that we're looking for. So once you do all that multiplication and changing the sign, you should get positive 2043. Subtract your other values. And for your final answer, you should get negative 105 kilojoules. So fairly simple. All right, chapter 7. Is everyone okay? Okay. Yes, this was chapter 6. Make sure you all know the Q equals M cap type problems. I didn't put that in the practice questions just because that's mostly plug and chug. So if you know Q equals M cat and they'll give you the values, you just plug them in. Okay, so for chapter 7. So for this chapter, I do have a worksheet. This is how I visualize it in the class. If it doesn't help you, then, I mean, you don't have to use it. But now I have to. Okay, so, and I'll move it around so you all can see it better. So this is pretty much your electromagnetic spectrum. So you have your radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. So make sure you know the order of that electromagnetic spectrum because those are easy questions. You don't want to miss that. So on this side of the equation, on this side of the spectrum, you have your lower energy. You have your lower energy, right? With low energy, your wavelengths are going to increase. So this is your wavelength. Lower energy, your wavelengths are going to increase. If your wavelengths are longer, you're going to have lower frequencies. So the longer the wavelengths, the less waves you're going to have per unit time. Also make sure you know the visible spectrum. On the other side, you have your higher energy. So for your higher energy ones, your wavelength decreases. As you can see, the waves are getting closer together. Because your wavelength decrease and they're closer together, you can have more waves per unit time. So you have an increased frequency. So make sure you know the relationships between energy, wavelength, and frequency. So frequency and energy are directly proportional. As one goes up, so does the other. And wavelength and frequency are inversely proportional. And this one should be on the SARC website as well. You can take it after if that's okay. Okay, so this one has a laser pulse, and then it's asking you for the number of photons. It gave you wavelength and energy of the pulse. All right. So our wavelength is equal to 337 nanometers. And we're just going to convert that to meters. So 1 nanometer is equal to 10 to the negative 9 meters. As you can see, we've done conversions in almost every problem, so make sure you all know how to do that. So now we have our wavelength in meters. You need to know that E photon equals hc over lambda. H is a constant, C is a constant. Now we just need lambda, right? Or E photon. So we plug in our constants. Oops. So C is 3 times 10 to the 8 meters per second. And then we already solved for lambda. And then once we figure out our answer, that'll be 5.8985. So that's our energy of the photon, right? Then with energy of the photon, you need to figure out the number of photons that you have. The equation for that is number of photons equals E pulse over E photon. That one I would make sure I know that. E pulse over E photon. They already gave us E pulse in the problem. And we just solved for E photon. And you should get 6.49 times 10 to the 15 photons. Okay, so for number 3, your professor gives different equations for how to solve this problem. It's not the way I learned it, but you should still get the same answer. So it gives you your final energy level, your initial energy level. It tells you that the hydrogen atom makes a transition, and you want to find the wavelength. So first you need to determine what's N initial and what's N final, because if you don't get that, it's going to be, your answer is going to end up wrong when you do the math. So your N initial is 6, that's where we started, and we're going to N final, which is 5. So the change in energy of an atom, and this is the part where I'm saying that your professor, I know, had a different equation for this, but it's the same thing. I think at least this part of the equation looks similar to everybody. But for this first part of the equation, I think your professor had something like negative HC something. Do you guys remember? Do you guys know what I'm talking about? Those HCR, I think it was like R or something like that, all of those are constants. So when you multiply out all of those constants, you get this number. So it's the same thing. If you're comfortable using the variables, then just continue with that. You shouldn't get it wrong as long as you're doing the math correctly. Okay. So then we're just going to plug in our N final and N initial. Final was 5, initial was 6. Once we do that, you should get negative 2.6644 times 10 to the 20 joules. So that's the energy of the atom. But when the atom loses its electron, it jumps energy levels, it releases a photon. So the energy of that photon is the opposite of the energy of the atom. So then all you have to do is change the sign of E atom that we just got, and you should get the same answer, just positive. Oh, oops. So that was the energy of the atom, but it wanted the wavelength. So this problem is actually not done. So we're going to go one step further. So that's energy of the atom, energy of the photon. And we know that energy equals hc over lambda. Since it's asking for lambda, lambda equals hc over energy. We already have all of those values, so now all we need to do is plug in the numbers. Okay, plug that in, and you should get 7.46 times 10 to the negative 6 meters as your wavelength. So first we solve for energy, and then plug that in for hc over lambda to find wavelength. Okay, so for number 4, it says, what is the de Broglie wavelength of an electron traveling at a certain speed? So this problem's pretty easy as long as you know the equation. So our equation, they gave us, first of all, so they gave us that velocity is equal to 2.65 times 10 to the 6 meters per second. De Broglie wavelength equation equals h over mv. This is the same h that we've been using, it's just going to be different units this time. The mass is going to be mass of an electron. I don't know if that's going to be given, but that number doesn't change. So mass of an electron is 9.11 times 10 to the negative 31 kilograms. Velocity was also given. When you multiply all that out, you should get 2.74 times 10 to the negative 10 meters for your wavelength. So I don't see de Broglie wavelength getting much more complicated than that. They'll give you, a lot of these values are already given, and then you're just plugging in the last value that they gave you. Okay, for the last one for chapter 7, this question wasn't worded that well, so sorry about that. It made sense in my mind, but then I read it again and I was like, oh, that does make sense. But we're going to go over it anyway. So this has to do with your orbitals. And it wants to know the quantum numbers of each of the orbitals in n equals 4. So our quantum numbers are n, L, ML, and MS. So our n is 4, because they told us that we're in energy level 4 already. our L is equal to 0 up until n minus 1. That means our values are going to be 0, 1, 2, and 3. And remember that each of those L values also corresponds to a shape. So O is S, 0 is S, 1 is P, 2 is D, and 3 is F. So then our ML values for each one, for S it'd be 0, for P it'd be, well, let me first write that ML is equal to negative L to L. And once you get how to do this, you probably won't even have to go through this whole process. Most of you all have this memorized. So for S, we have 0. For P, we have negative 1 to 1. For D, we have negative 2 to 2. And for F, we have negative 3 to positive 3. Our MS is either positive 1/2 or negative 1/2. So we're going to have 1 4s orbital, 3 4p orbitals. And you can tell because in our p we have negative 1, 0, and 1. So that gives us 3 4p orbitals. We're going to have 5 4d orbitals and 7 4f orbitals. Now what you can do is add up all these orbitals, 1 plus 3 plus 5 plus 7, and that's going to give you 16 total orbitals, or just know that n squared equals total orbitals. N squared equals the total number of orbitals. Our n was 4. You get 16. All right. On to the next one. So chapter 8. Chapter 8, I also have, Chapter 8, there's also a review worksheet that is on the SARC website under my name. Basically what I have here is well, anyway, I have the trends on the periodic table. So as you go across, what happens to radius, metallic character, ionization energy, electron affinity. So I have the trends for that going up and down. So if you want, you can take a picture after the session, or this is also on the SARC website. So I would really make sure I know these trends, or else it's going to be really hard to figure out some of these problems. All right, so for number 2, it asks for the noble gas configuration, the orbital diagram, and whether the atom is paramagnetic or diamagnetic. And that's going to be for beryllium. All right. So for beryllium, which is number 52 on your periodic table, you can look for it there. So beryllium, I'm going to start out, I'm going to do the noble gas configuration. So the nearest noble gas think that's krypton. That's going to be your noble gas configuration. Your orbital configuration is where you're going to draw in your boxes. Okay, so you have 5s, you have your 4d, and you have your 5p. And this whole process is pretty easy if you know how to do it using the periodic table. So then we're going to put in our valence electrons. You want to follow Hund's rule for all of them. You put in one arrow in each box, and then go back and fill the boxes. That's 4d10. And do the same thing for your p orbitals. And then for paramagnetic and diamagnetic, make sure you do Hund's rule, because that did happen to me once where you kind of rush through and don't do Hund's rule, and then you miss paramagnetic or diamagnetic. So diamagnetic is when all of your electrons are paired. In this case, we have 2 electrons that are not paired, so this is going to be paramagnetic, meaning you have unpaired electrons. All right, for these next few problems, if you have like your phone or your laptop, I would suggest looking at a periodic table while we do them, just because it's kind of hard for me to show the periodic table up here. But, so for number 3, it asks you to choose the larger atom in each ion pair. In each pair. So for these, you're going to need to know what your trends are for ionic size on atomic size on your periodic table. So if we're choosing between N or F, okay. So right here, N or F, we know that N is going to be the larger atom. N is going to be the larger atom based on the periodic table trend. The atoms get smaller as you go across to the right. For B, you have C or GE. If we quickly look at this, here's C, here's GE. Ionic size increases as you go down, so GE is going to be the larger one. For letter C, you have N or aluminum. You want to look at, there's N, and here's aluminum there. It's below it, and it's to the left, so aluminum would be larger. And for D, you have aluminum or GE. Here's aluminum. Here's GE, and you have opposing trends because it's to the right, which would make it smaller, but it's also below, which would make it larger. So in this case, you wouldn't be able to determine. And it's okay to have an answer like that. I don't know if she would make it an option, but if you had something like this, it would have to be cannot determine. But I don't know if she's going to exactly put that on the test, if that makes sense.
And then what were the qualifications for it being undetermined again? If it was,
If it's opposing trends. So GE was below, but it was also to the right.
okay.
So one's making it larger, one's making it smaller, so in that case you can't determine.
Okay.
All right, so the next one is asking for ionization energy. And it doesn't matter that it says higher first ionization energy. That's not going to make a difference in this case. So for number 4, we have Al or S. So if you look at Al and sulfur that's over here, ionization energy increases as you go to the right. So sulfur is going to be the the one with the higher ionization energy. For letter B, it's either going to be AS or SB. And those two are right here. AS is going to be the larger one because ionization energy increases as you go down. The next one is N or SI. So SI is to the left and below N, which would give it decreasing ionization energy. So the bigger one would be N. And the last one is O or Cl. Cl is to the right and also below. So then in that case, you have opposing trends. So again, for this one, you wouldn't be able to determine it. And then for number 5, so the last one, it asks for the electron configuration for each ion and to choose the larger atom. For this one, I'm only going to, because we already did electron configuration earlier, we're just going to choose the larger atom or ion in each pair. So the first one is S or S2 minus. In this case, the anion. The anion is going to be larger than both the neutral atom and the cation. Calcium, or its cation, your neutral atom is going to be larger. And finally, Br minus or Kr. So these are called your isoelectric elements because, as you can see here, once you take away once you add that electron, it becomes like Kr. So in this case, bromine is larger. So remember that cations are smaller than the neutral atom, which are smaller than anions, or positive and negative charge. So if you can just remember positive and negative charge is always the bigger one. All right, so we have about 20 minutes and 2 chapters left. So let's see if we can finish this. All right. So chapter 9, you learned about lattice energy. So make sure that you also know the trend for lattice energy on your periodic table. Or just lattice energy in general, I should say. Okay, so it wants you to arrange these in order of increasing lattice energy. Okay, this is chapter 9, number 1. So what I like to do is arrange them by charge first. So starting with charge, we're going to compare the ones that have a positive charge, which would be KCl and KBr, because they both have a +1, -1 charge. And then we also have, we can compare calcium oxide and strontium oxide. And these are your +2 charges. So right away, when you're dealing with lattice energy, try to compare them by charge. The one with the higher charge, which would be these, are going to have the highest lattice energy. So that's going to tell you right away that these are already smaller than those two. But then now we can break it down further based off of the size of the atoms. So for that, you're going to have to look at your periodic table. So these both have potassium in it, so we're going to compare chloride and bromine. So Br is below bromine, making it a larger atom. So the larger the size, the smaller it's going to be. Smaller lattice energy, I should say. So it's larger, so it has a smaller lattice energy. So our first one in the sequence is going to be potassium bromide. That's the smallest one. Then we have potassium chloride. Now we need to compare, oxygens are the same, so now we need to compare calcium and strontium. Strontium is below calcium, making it the larger atom, so that's going to have the smaller lattice energy. So this one's larger, so it has a lower lattice energy. So that's going to come next in our sequence, and then calcium is the largest lattice energy. So this is how you would order based on lattice energy. All right. So number 2, for this, I would expect probably the electronegativities to be given, just because some of these are a little more difficult to figure out solely based off of the trends. So she'll probably give you the values for a question like this. So it wants you to tell whether it's pure covalent, polar covalent, or an ionic bond. So Br and Br, those are the same. So for that, you're going to have a pure covalent. For carbon and chloride, you would have to know the difference in electronegativities, so to know that that's a polar covalent bond. Carbon and sulfur is pure covalent. They both have an electronegativity, I believe, of 2.5. But if you had just looked at the periodic table, you wouldn't have known that. So for a question like this, like I said, I'd expect the values to be given. Or she may be asking you all to memorize it. You know what she said in class. I'm not sure. All right, and for the last one, you have a metal and a nonmetal, so that's ionic. So you don't need any numbers for that last one. All right, number 3. So this is where we're going to get into drawing Lewis structures for some of these. All right, so it wants you to assign formal charges and figure out all of the possible structures. So for this first one, phosphate, we'll start with phosphorus in the middle. And for these, make sure that you remember, oh, you can't see it, sorry. Okay. Phosphorus, make sure that this is PO3 or PO4. Make sure that you remember that elements that are below period 3 and below can have expanded octets. So they are allowed to break the octet rule. So since they're allowed to break the octet rule, we're going to move one of our lone pairs and make it into a double bond. And this is an ion with a 3- charge. Not going to draw the resonance structures, but for the resonance structures, just know that the double bond can go with any of these oxygens. So those would be your resonance structure. Double bond here, then double bond there, then a double bond right there. Okay, the next one is Cn-. Make sure that you count how many electrons that you're working with, because with this minus charge, you're going to add one more valence electron. And this one doesn't have any resonance structures. The next one is SO3 with a 2- charge. Your S is going to go in the middle with the 3 oxygens surrounding it. Then you have your lone pairs. But then you'll notice that your sulfur doesn't have an octet. So what you're going to want to do is move one of the lone pairs and make a double bond. So now our sulfur has an octet. Again, this has 3 resonance structures because the double bond can go in between any of these oxygens.
So sulfur has 6 valence electrons, right?
Yes.
So, and that's sulfur 2-, and I'm only seeing 3 valence electrons around that sulfur, and then 4 if you count the double bond. I'm just confused.
3 valence
I'm
electrons?
sorry, it's like, so there's 6 bonding electrons with sulfur, right?
Your number of valence electrons is not the same as the number of bonds that you're going to form, because you want to form an octet. So you want to make sure you have your 8 electrons surrounding sulfur. If you still have a question. Mm-hmm.
Okay, for the one with phosphorus, the PO4, how come it's like a double bond for the octet relationship?
Because remember, there's elements that can break the octet rule. So elements in period 3 and below, you can have an expanded octet. So you're allowed to have more than 4 bonds.
Okay, so do you have to have more than 4?
In this case, the reason why you did that is because this gets your formal charges to be 0. So you want to get your formal charges as close to 0 as you can. Okay? And the last one, ClO2 minus. You're going to have chlorine. And there's no charge on that. Oh. So those are the Lewis structure problems. I think we have a few more when we're trying to figure out electron geometry. So for number 4, a lot of the values for these kinds of problems where you're finding bond energy, those are going to have to be given. So what I do for these types of problems, what I like to do for those types of problems is draw out the molecules, because then you can tell how many bonds are being broken, how many bonds are being formed, and which bonds those are. So make sure you all practice Lewis structures, because again, this is one of those problems. If she didn't draw it out for you, it'd be really hard if you didn't know how to draw it yourself. So you see that you have 4 CH bonds, and this side is your bonds broken, and the other side are your bonds being formed. So we have 4 CH bonds. Each CH bond has 414 kilojoules of energy. That number would have to be given to you in some way. Multiply that by 4. For your OH bonds, you have 4 OH bonds. Each OH bond has an energy of 464 kilojoules. So we're going to multiply that by 4. You also have 4 H bonded to H bonds. And the number for that is 436 kilojoules. And we're going to multiply that by 4 again, because we have 4 of those bonds. And then we have 2 carbon bonded to O with 799 kilojoules per carbon bonded to O. So we're going to multiply that by 2. So then when you multiply all of those energies, your delta H of the reaction, and I think your professor gave you a different equation for this, but it'll be the same answer. But what your book gives you is the sum of the delta H's of the bonds broken plus the sum of the delta H's of the bonds formed. That last word is formed. If you do it this way, you have to take into account which ones are positive and which ones are negative. I think the equation that your professor gave you was bonds formed minus bonds broken, right? Anybody know? It was? Oh, okay. Well, either way, you should be able to get the same answer. So you get 3,512 minus 3,342. And that'll be your final answer. So energy is released as you're forming bonds, so those values are going to be negative. But depending, like I said, depending on which equation she gave you, was it this one?
Bonds broken minus bonds formed.
Okay, yeah. So if you just do bonds broken minus bonds formed, it's the same thing. Then you don't have to worry about changing the sign of the numbers. All right, we have a few more minutes, but we can still try and get through chapter 10. Okay, so the first one, I'm just going to skip the first one because it's a lot like the second one. So the first problem is a lot like the second problem, so I'm just going to go straight to the second problems. So this is chapter 10. And to find molecular geometry, I don't know how you would do that without drawing the Lewis structure first. So again, make sure you know how to do that. Iodine is again one of those elements that can form an expanded octet, so it does not have to follow the octet rule. And you'll notice that you have extra electrons that you have to work with, so then you just add them on to the central atom. But that's only for elements that can form the expanded octet. So we're going to count our number of electron groups: 1, 2, 3, 4, 5, 6. So you really need to know that table in your book. I believe it's table 10.1 or 10.2. If you have 6 electron groups, make sure you have memorized that that's going to be octahedral for its electron geometry. And electron geometry is only based on the number of electron groups. It doesn't matter if it's a lone pair or not, solely on electron groups. Its molecular geometry, however, is going to change based off of the number of lone pairs. We have 6 electron groups, 2 lone pairs, that's square planar. Again, that's just whether or not you have the table memorized. All right, so for the next one, let's try to go to problem 3. PCl3 would be the same thing. You just draw it out, figure out how many electron groups that you have and how many lone pairs that you have. So let's just go on to number 3 to save time. So it gives you methanol. CH3OH. So you're going to want to draw that out. So you look at each interior atom, carbon and oxygen. Carbon has 4 electron groups surrounding it, 1, 2, 3, 4. So that's going to make it a tetrahedral. Oxygen also has 1, 2, 3, 4 electron groups, but it has 2 lone pairs. So 4 electron groups and 2 lone pairs you need to have memorized is bent. So each interior atom has its own electron geometry and molecular geometry. All right, number 4, it's asking about polarity. And I'll just draw that quickly because I really want to get to number 5. So number 4, it's asking about CClF3. If you draw that, all of the fluorine atoms pull on carbon with the same electronegativity, except for chlorine. Chlorine has a different electronegativity, so that would tell you that the molecule is polar, because these 3 atoms are pulling more than chlorine is. Okay, and let's try to quickly do number 5. So it's asking about BRF3, and it's asking about the hybridization. So hybridization, I would know the table in your book. Let me see. It's table 10.3. So table 10.3 gives you a list of the hybridizations, so I would just know that. So if we quickly draw out BRF3, okay, and bromine has its expanded octet. It has an electron. It has 1, 2, 3, 4, 5 electron groups, meaning it's trigonal bipyramidal. And in that table 10.3, it would tell you that trigonal bipyramidal has a hybridization of sp3d. So make sure you know table 10.3 for hybridizations. And that's all we have time for. Hopefully this was helpful. If you have any quick questions, you can definitely ask me afterwards. But good luck on your exam, study hard, and I know you'll do well.